In this module, we want to give you some relevant terminology and a sense for how radio devices convey information in the form of electromagnetic waves. To set the stage, let's imagine how your phone connects to a wireless network, either cellular or Wi-Fi, and how it conveys texts and photos to the network and downloads web pages. How does that work? For the purpose of this module, we want to focus on the antenna and electromagnetic wave propagation. So let's focus on two antennas and a radio signal that might propagate between them. This radio signal is an example of an electromagnetic wave. Other examples include light and X-ray radiation. Electromagnetic waves obey some laws of physics called Maxwell's equations, attributed to the Scottish scientist James Clerk Maxwell. These equations relate the electric field E to the magnetic field B through partial differential equations in 4 variables, 3 spatial variables, x, y, and z, and a time variable, t. Solving Maxwell's equations in the general case is very involved, and we often resort to solving it via a computer. We won't be focusing on detailed solutions of Maxwell's equations in this class, but it's important to remember that electromagnetic waves must abide by them. There are some special cases in which we can obtain some good insights about the nature of electromagnetic waves. The simplest case is the so-called planar wave solution to Maxwell's equations. For this simplification, we assume the two antennas are separated by a large distance. If we label the direction of propagation with the z-axis and label the direction of the dipole antennas with the x-axis, then we get some interesting structure in the planar wave solution. First, the EM wave propagates along the z-axis from the transmitting antenna to the receiving antenna. Second, the E field oscillates up and down along the x-axis. We can think of this E field as being induced by an electric current that moves charges back and forth in the transmitting antenna, a topic we will explore in more detail in another module. Third, the B field oscillates back and forth along the y-axis perpendicular to the E field. Having described the planar EM wave qualitatively, it's worth emphasizing that there is a beautiful mathematical equation that governs the simplified solution to Maxwell's equations. We introduced this equation to highlight some key parameters of the propagating EM wave. The planar wave equation is shown here, focusing on the variation of the E field. We see that the EM wave is oscillating both as a function of space, in this case along the z-axis, and time, the t-axis. The particular type of oscillation is called sinusoidal. The two key parameters of the EM wave are how fast it oscillates in these two dimensions. The wavelength is the length of one full cycle in space when we take a fixed snapshot in time, and is often measured in units of meters. The frequency is the number of oscillations per unit time when we look at a particular point in space. Frequency is measured in units of hertz, named after the famous physicist who experimented with EM waves. It turns out that frequency and wavelength have to relate to one another because the EM wave propagates at the speed of light, 3 × 10⁸ meters per second. Some example frequencies and wavelengths are highlighted here. The set of all radio frequencies is called the RF spectrum. As we can see from this US spectrum allocation chart, different radio frequencies are used for a wide variety of applications. Now let's see antennas and EM waves in action in a simple laboratory setting. Here we have a simple transmitter which is generating a current back and forth in this dipole antenna. Based on the planar wave solution to Maxwell's equations, we would expect the electromagnetic field to be oscillating in this direction, aligned with the antenna. And here we have a similar dipole antenna that is connected by a flashlight bulb. If a strong enough EM wave impinges upon this receive antenna, it should generate a current back and forth in the antenna and light the bulb. When we power the transmitter and align the receive antenna to its induced E field, we see that indeed the light bulb turns on. We can use this simple hardware setup to demonstrate a few important aspects of EM wave propagation. First, the planar wave solution is relevant at fairly short distances. When the antennas are in alignment, the bulb lights up. However, when we rotate the transmit antenna 90 degrees, the light bulb does not light up. This is because the transmit E field is moving perpendicular to the receive antenna and cannot induce a current. Second, signal strength drops with separation distance, an effect we often call path loss. As we move the transmit antenna farther away from the receive antenna, the light bulb burns weaker than when we move the antennas closer together. Third, if we have more than one transmitter emitting an EM wave on the same frequency, the receiver picks up both of them. This is an effect called superposition, which results from the linearity of Maxwell's equations. That is, the effect of two EM sources is the sum of their resulting waves. Superposition leads to some major challenging issues in wireless technology. As one example, when a signal propagates from an antenna, it can bounce off of objects in the medium and result in multiple copies of the signal with different gains and time delays at the receiver. This effect, called multipath propagation, results from a transmitted signal interfering with itself because of superposition. Another example is two different transmitters whose signals are close together in frequency and therefore interfering with one another. We will see that both forms of interference represent major challenges in wireless that must be treated from technology, economic, and regulatory perspectives. EM waves are these beautiful, intricate interactions between the electric field and the magnetic field between two or more antenna elements. They are governed by Maxwell's equations. We can develop a fair amount of insight using the planar wave solution, for which the key parameters are frequency and wavelength.